We're going to continue our talk on how we can use machine learning for visual recognition. We saw in the previous lecture some concepts and some ideas on how to use machine learning for visual analysis, and we'll continue the talk today with more specifics. We'll look basically at some very popular algorithms and techniques that have been used throughout the literature for classification, for detection, and recognition. Specifically, we'll see how we can build recognition systems using different types of classifiers, as well as different types of features. We will see the Viola-Jones Face Detection algorithm. We will see how to build support vector machine classifiers for pedestrian detection. We'll look at the bag of visual words technique, and we will conclude with EigenFaces that is mostly used for face recognition rather than detection. So as we talked about in the previous class, visual recognition is basically the ability of a computer to understand what's in an image. We humans do it all the time, through looking at photographs or video, and we are able to spot different objects like cars, dogs, chairs, and so on. And the goal of visual recognition is to make a computer do exactly the same task by looking at an image. So as we saw in the last class, we want to do that for different reasons. First is because the real world is challenging, and objects can appear under different illumination, different deformation, and through a lot of clutter. So there's a difficulty in trying to hard code this into a computer. For this reason, we want to look at the data and learn from the data so that we can build more general systems. To successfully use machine learning, what we need to have are, first of all, good features that can be described in terms of the class. We want a way to measure how well we are doing when we are learning. So basically, if we are learning the right things, and if we are have a good accuracy with respect to the task we want to achieve. And that is done through a loss function or an objective function, which we use to let us know if the model is doing well or not. And another aspect is that we want to have a way to tune the parameters of the model so that we improve our performance. And this is done through the optimization process. So the most frequently used machine learning approach today for visual recognition is supervised classification or supervised learning. In this paradigm, we have a collection of labeled examples, the image with its respective class. And since we know what these classes are for our training data and our test data, what we want to minimize is the expected misclassification. In other words, the mistakes that the classifier is doing, and we want to make it as accurate as possible. There are two strategies to do that. The first one is called generative. In this paradigm, what we do is we first model the probability of each class. So for example, here, if we have the number 4 and number 9, we make a model for what is number 4, and we make a model for what is number 9. And then when we have a new input coming in, we just try to find which of the two models describes that particular input better. The other approach now is called discriminative. And we basically, in this paradigm, we directly construct a good function, a decision boundary, based on a function to discriminate between the two classes. So let's start with the generative approach first to understand how it works. So in this paradigm, we want to model two classes. for example, number 9 and number 4. And basically, what we have is something like in this image right here, when you can see we have the model, the probability of having of feature value belonging to the number 4, and the probability of the feature value belonging to the number 9. So intuitively, the best decision boundary, the best threshold is at the middle, where the probability of each or the other one is exactly equal. So we are not sure, basically, from the data which class the points belong to. Imagine that if we put it all the way to the left, then we will misclassify a lot of number 4s. If we put it to the right, then we misclassify a lot of number 9s. So we need to find a balance and the best trade-off between basically how many values we want to misclassify. So to model that, we have basically a model that tells us what is the probability that our feature value is actually a number, in this case, number 9, and what is the cost, basically, of mislabeling number 9 to a 4. So what is the cost of making a mistake? So given that we assume that we have the same cost either way, if we mistake a 4 for a 9 or a 9 for a 4, then we can choose the best class that this feature belongs to by looking at which of these two values are bigger. So basically, if the probability given the value that it's 4 is if it's higher than the probability of given x that is a 9. So the question is, how can we find out what these probabilities are? Of course, since we're doing machine learning, we can use data to find those probabilities out. So let's consider an example here of skin detection, where we want to label each pixel in the image as being a skin or not. So skin color, it's basically used for detecting people, and a discriminative feature of skin color is hue. Okay, so we assume first that we have a data set that someone has labeled. So someone has actually went on and marked every pixel that belongs to a skin in some images. And we then built a histogram of our feature, which is the hue of the pixel. And this histogram tells us what basically, if it is a skin, what is the probability that, given that it's a skin, to have that specific value of hue. Okay, so basically this is the probability of observing a particular hue value. Oops. So the question is, what we are looking for basically, however, is this. It's the probability that given the hue value, if it's a skin or not. And this can be, we can find it out using the Bayes rule. So the Bayes rule, basically, it's what we call the posterior that we want to find is equal to the likelihood, which is the probability given that it's a skin to have a particular hue value, multiplied by the probability of having a skin. And this is a normalizing factor here to make this output as a probability, but in many cases, we just assume that they are analogous and we remove this factor here. So we're left with the likelihood times the prior. So the likelihood is basically is what we compute with the histograms. So we have this quantity here. And the question is, how can we find out the probability of having a skin pixel? Well, this again can be done through the data. And also note that since we have the probability of having a skin pixel, adding the probability of not having a skin pixels should give you to sum to 1. Also note here that in the histograms, we do have some overlap between the two classes. And hopefully, we hope that by making, by having a distribution rather than using individual pixel values, we can have some structure that the machine learning algorithm can utilize to avoid these overlaps. So now that we have those values, we can apply directly the Bayes rule, and we can tell if a pixel is a skin or not. So basically, we do the likelihood ratio test, assuming, of course, that the any errors that we make are the same regardless of what is the type of error. Otherwise, we have to reweigh the two values. So basically, if the probability of being a skin pixel, given of having this particular hue value given that is a skin pixel is higher than having this particular hue value given that it's not a skin pixel, then the hue value is classified as skin. And we can use that rule to make it simpler by just having a threshold, and we can classify pixels as either skin or not. And incidentally, this particular approach using the Bayes rule was used in a perceptual user interface that you see in the picture here, where the brighter colors, the brighter pixels correspond to what the classifier classified as pixels, skins. So you can see, for example, that the eyes were the areas where we have the glasses on top of the ear that was not so visible, and the classifier deemed that to be not skin pixels. So looking at generative models, we can have also more than two classes. What you do in that case is you just basically model all the data points of that particular class. And for each new point, you check its probability in belonging to that class, and you select the class that gives you the maximum probability, basically. So we generalize the two cases. We can also have continuous generative models. So in images, we have pixels, which are discrete. We can also have continuous values. And in that case, we need the likelihood for the density model of the probability of observing X given the particular class. And in such cases, we usually approximate that using some Gaussians or mixture of Gaussians. And this is advantageous since we can do this process using only a small amount of data. So in the example here, you can see we model one class with a Gaussian, and the other one we can model it with a mixture of Gaussians if it's more complex. This was just a brief introduction to generative models, just to grasp the intuition and the idea behind the different approaches. So the good thing with the generative models is that they have a firm underlying mathematical formulation, which stems from the fact that these models have basically been worked on before we had a lot of compute power, so people had to be smart with their math on how to extract knowledge. It allows us to extract prior knowledge from the data and incorporate it into the classifier. So we can, the fact that we know that most pixels basically are not skin, we could add that into the model. We can have a parametric modeling of the likelihoods, which it fits well when we have a small number of data. When we want to add new classes, we can do it effortlessly without having to do anything with the previous models. We can even improve the previous models and not have to change much in our algorithm. And interestingly, when you have a probability of what values belong to a particular class, you can use that model to generate new examples. And this is why, of course, these are called generative models. On the other hand, these models are not that popular, especially with big data, because even if they allow us to have priors. We're not sure if those priors that we choose to use are the best ones. And basically, we're modeling also maybe points that we're not interested in. So one could ask, why do we have to model then the non-skin pixels in the example? Non-skin pixels can be everything, so maybe it's impossible to model them. So it might make more sense to model the hard examples near the boundaries with the class we're interested in. Also, as I said, the fact that they work well with little data means that basically when you have a lot of data, since you are fitting a particular model, it might not be able to utilize all that data. So it doesn't leverage big data that much. So general models, as I said, were the first approaches used for classifiers. Since then, we have developed different models and different approaches. The major limitations of the generative models is that as we increase the feature space, it gets exponentially hard to model and to find good models of data. So for these reasons, people have started to look at discriminative classification methods. So for discriminative classification methods, we basically have some assumptions. We assume that we have a fixed number of classes, of known classes. Of course, we assume that we have an ample number of training data. Otherwise, we have to deal with these approaches differently. We assume also that the cost of a misclassification it's no different than any other. So all misclassifications are treated equally. What matters instead is that we want to get the labels of the class right. And we need to construct a representation of the instance we want to identify and classify. But we don't know beforehand what is good and what is good in terms of features. So the general framework, as we saw in the previous class, is basically this framework where we first train a model, and this involves building a representation of our data. So finding what are good features to represent our data in order to describe the training images and the instances that they contain, and extract feature vectors that come from the images. In that way, then, we can basically use those features to train a classifier. Once we have trained the classifier, we can test it on new images, score the images, and evaluate how a model does in terms of accuracy or another metric. So in this process, we first have the image pixels, we do some feature representation, and then we train a classifier to predict the class labels. So first, let's recall what are maybe some good features and what are their advantages and disadvantages. So we assume that we have a whole context of the image. So we assume that the image is located in the image we want to classify, and we want to build a holistic descriptor for the content of the image. So let's think about what will make some good representations for using training. So basically, the representation we want to find is in order to discriminate between the two classes. Now let's see some possible choices. So we have, first of all, pixel representations. We can take the pixel values of the image. We can arrange that into a vector, both for color and grayscale images, and use that as our feature to train a classifier. Now, of course, this is not a good idea because changes in pixels in terms of illumination can yield many a very different feature. And also, if the object moves a bit, then we still have, will give us a very different feature. So if we instead use a color histogram, then might be, if in this particular case, as you can see, the two objects are discriminated, but it's still not a robust solution. So if we have a shift in the object from the image, then it will change our histogram. So we'll have a lot of intra-class variability in terms of the feature. So if you remember when we're doing Harris detector and motion detection, some robust features that were so to stay where they are when the illumination, so they're robust to that. But again, if you have some small motion, then this basically changes your features. So another feature that we can use is to do some histograms locally. So we do what we call we do locally orderless histograms. Basically, we take a picture, we find the gradients, we break it into blocks, and for each block we build a different histogram. So locally, our representation is does not have any spatial information, but globally we retain some form of the image. So if the object moves a bit to the left or right, or forward and backwards, then the information in each of these local histograms is retained. So our representation is more robust to motions. So we have these representations. Now the question is to train a binary classifier, basically using these features to tell us if it's koala or panda in the image. And of course, we always assume here that we have some annotated database that we can learn on. And now the question shifts to the classifier, basically. So a binary classifier can select between one of two classes, and we have different choices. So we saw in the previous class, for example, we saw the nearest neighbor classifier. Here you see some other popular methods for building classification systems. You can see also some references for these systems below. So the general approach in all these classifiers is to find first the best feature vector and use it then with one of these classifiers to train them to detect what you want. And we're going to see some of these classifiers in this class, and some others in the next lectures. So we have this pipeline of getting data, finding a good representation, and building a classifier. So once we have this classifier, we can then get an image from the data that we had before, find a good representation, extract the same representation from the new image, and feed that to the classifier to tell us if it's what the label of the object is, basically. So the interesting thing is that we can repurpose this classifier into an object detection system by just basically looking at local regions in the input image and classifying them individually. We can turn a simple classifier into an object detector. And this approach is called the sliding window approach. So let's consider here face detection as an example. So we have this input image here, and we want to look for faces. So what we do is we slide a window over the image and classify each and every one of those blocks that we extract in the image. Now, of course, as you can see, some of the faces are smaller or bigger than the window. So if they are bigger, they won't fit in the window. So we're not gonna give a chance to the classifier to see the whole face. So to tackle this problem, what we do is we have a pyramid of images. So we downscale the image that we get into smaller versions, and then we extract blocks from each and every one of these versions. And what we get are candidate search windows. So this can generate thousands of small windows from the image. So for each and every one of the windows, we then do the pre-processing or feature extraction as during the training phase, and we feed it to a classifier. Now the classifier will say for each and every one of these blocks if they are contain the object we're looking for or not. And if they do, what we do is we basically mark their scale that we found them and the size, and we project that back into the original image, and we draw a bounding box around the objects that we found. And this is basically how object detections worked up to a few years ago. So this is basically a very recent way of building a detection system. So it's interesting to see here that our classifier essentially sees very small chunks, a lot of very small chunks in the image at different scales. And this has been the dominant paradigm in computer vision for a few years, up to a few years ago, until deep learning came in. And it's based mostly on local information, because we see every patch isolated from the other and independent from the other. And we will see in later lectures how we can improve on this. But for this lecture, this is the framework we're considering. So the job of discriminative classifiers is to find a decision boundary, a surface to separate the classes in the feature space. So there are several methods that we can use to do that. We saw in the previous class the nearest neighbors. We talked a bit about linear classifiers, and today we're going to talk more a bit about support vector machines and boosting methods. Okay, so just a reminder on nearest neighbors. So nearest neighbors rely on the whole training set to classify an image. Basically, we choose the label of the nearest point that the new input falls to. So if a point falls here, then we will just classify it in the same class that the other its neighbor it belongs to. An extension of that is the k nearest neighbor. In the k nearest neighbor, basically we don't consider only one of the neighbors, but k. In this case, k equals 5. So all the neighbors vote on the class of the new point, and the majority wins. And for this, it's important that we don't have even numbers, but odd numbers. So 3, 5, 7, etc. But of course, it's data intensive problem. So we have to, the more neighbors we have, the more points we have to check. And this is an illustration of what the k nearest neighbor will do. So on the left, you see some data samples from a very popular data set, the CIFAR10 data set. And on the right, you see some test samples and what is selected as their 10 nearest neighbors. So it's really interesting to see that for the first row, for example, we have the track here, and we can see some horses there that have been identified as being close. So it's just to emphasize that what we look in an image, what a computer looks at and selects is quite different. So let's talk a bit about the nearest neighbor classifier. One final point. So we have the data on the left, and we have different options of selecting our k. So which one would possibly be a good case. So we look at the middle with a single nearest neighbor. There is a lot of small islands in the region that it forms. So we would say that this is not robust to outliers. So if you look at the data, you could see that some blue dots are here and there, and they seem to be outliers. This could be because of noise or some even wrong annotation in the data, and so on. So we can see that the 5NN classifier gives much more robust results. Okay, so moving now beyond the nearest neighbor classifiers, we also talked a bit about linear classifiers. So the simplest form of a classifier that has learnable parameters, because remember the nearest neighbor classifiers do not have any parameters. They only use the whole data set for inference. So here we have basically a model that models a line, and we are looking for the values of the vector W and B so that we can classify these two data sets using a line. And in higher dimensional spaces, like 3D, this line is called a hyperplane. So visually, what happens in a linear model, in a linear classifier, is we assume that we have, for example, in this case, 4 pixels in our image. And basically, we have the vector W that we multiply with with our input image, and we get some results. And at the end, we have the class probability. So in this particular example, what we also show here is that you can have multiple such classifiers. So every row in the matrix W is a different linear classifier. So at the same time, we get some results for different classes as well. So for the first class, the example here is in the cats versus dogs example, it's negative, so it's classified as a cat. So when you have multiple linear classifiers, this is what it basically looks like. The weights can also be viewed as a template for each of the class. And it's interesting to see, for example, the sheep class. Its weight has more of a blue color, so it responds well to images that have sheep, for example. Or the horse template, you can see that there are 2 different heads of the horse in opposite directions. So you can see that the vector W that is formed through the linear classifier has some meaning and some intuition behind it. So when we talk about linear classifiers, it's useful to talk about the distance between the lines, the separating lines that we want to find, and the point. So we have our line here that discriminates between these points, and we describe this line through the line equation, and we have a point x0, y0, which has some distance from that line. And we're interested to find how far away from that line is a particular point. So for the line, we also have a vector W, which is perpendicular to that line. So we can basically rewrite this equation here using that vector W. And when we do that, there's some formulations that show that you can find the distance between the point x0, y0 using W. Basically, this is using some vector projection, and I have the link there. You can find how to derive this equation. But at the moment, it's important to know that that is the particular equation. And also, we can use, we can assume that this equation here, Wx plus b is 0 for every value, for any value of W and X. So basically, we can scale them accordingly, and we can still get a valid equation. So it's a good question to ask that if we want to build a linear classifier, basically in the form of the Wx plus b that separates the negative from positive samples, what is a good line to choose from? So this could be a valid line. This could be a valid line. This could also be a valid line. This could also be a valid line. So there are many different options that we can use. The question is, which one of these lines is the best in order to discriminate between the classes? And this is where the support vector machines algorithm comes in. Basically, SVMs, as they're abbreviated, are a specific formulation on how to decide which separating line is the best for a given data set. So SVMs basically, they find lines that lie at the same distance between each of the two classes. So we have the boundary of one class and the boundary of the other class. And the best line, as found by SVMs, lies in the middle of these two lines. And we call this distance that between one boundary and the other boundary as the margin. So they define this notion of margin. So what we want to achieve basically is to maximize the margin between one class and the other class. So we can find the best possible line. So we assume that the line in the best separating line is given by equation Wx plus b equals to 0. And remember, we can achieve this because we can scale W and X according to and also B, so that we can always assume this, that this is true. And we assume that the lines that are at the boundary of each class are given by XW plus B equals -1 and Wx plus B equals 1. So, and we want to basically find the value of W and B so that for every positive class, we had that value of the equation W plus W times X plus B is more than 1. And for all the negative examples, Wx plus B to give us less than 1. So if you look at the diagram, there are a couple of special points here. So these are the points that lie exactly at the boundary. So they basically, and this is why they're called support vectors, they support the boundary of each class. So if you look at those points, these are the points for which the equality is true. So they are exactly equal to plus or minus 1. So if you want to find the distance between these two points, essentially we're finding the distance, the margin, basically. So if you recall that the distance of a line and the point is given by this equation right here, and we know that for support vectors, this is exactly equal to plus and minus 1. Then if we find the difference between the distance of one point and the distance of the other point, it gives us exactly what the margin is, which is 2 divided by the norm of the vector W. So we say that basically we want to maximize the margin by finding a small value for W. So this is exactly, we're looking for a value of W, basically, that minimizes the margin under the constraints that were given positive and negative labels for each of the classes. And we can write this as the following quadratic optimization problem. So we minimize, so notice here that we went from a maximization problem here into a minimization problem. So these two are equivalent. So if we maximize W to minimize margin, it's the same as having to minimize W, which again maximizes the margin. So we want to minimize W, the margin, the norm of W divided by 2, subject to the constraints that the label of each point multiplied by W x plus B is greater or equal than 1. So basically what this constraint here does, it's merging together the two other constraints into one, if you do the math. So basically the plus and minus sign of the label inverts the constraint every time, so we can only write it with one line like this. So what we just described, this formulation, is called the hard margin classifier. So even in some books, you will find these are just, you will see that it is called just a hard margin classifier. So basically, we want to find this constraint and want to classify all our data points correctly. So what if we want to basically say, okay, we have some points that may be outliers or maybe mislabeled. How can we deal with those? And in that case, what we do is we have we add a penalty term that is used to allow for some mistakes, but we can also penalize mistakes. So we do that using the parameter C. Basically, it controls how many misclassifications we allow. So if we have a high value of C, this means that the algorithm will try to make the sum, to bring the sum to a low value, so it can overall decrease the objective function value. So if we have a small c, it means that we can have more, we can allow for more mistakes. And this formulation is called the Hinge loss formulation. So basically, if you look at the max function, it's only activated, that is, it's greater than 0 only for samples that are beyond, that are on the opposite side, that are on the wrong side of each of the class. Okay, and you can see it here that basically it gets 0 when you have correct classifications. And again, you can use the C value to control the whole process. There is another formulation that is quite similar. You can find it in some books, which is called, which is basically uses slack variables. It's the same idea, but rather than having a hinge loss to give you a penalty, there is this slack variable Z that you can adjust its value so that it makes data points seem to be classified correctly. And again, the more Z values we have that are non-zero, it means we allow for more classifications to be wrong. Okay, so now we have a formulation that allows for to find the maximum margin and for some errors. How do we basically come up with a value of WB? What are the actual values that we need to use? So we can basically use the Lagrangian Multipliers technique. It's a technique that is used to find local maxima or minima of functions. Basically, it says that if we have a problem of the form minimizing f, x, and y subject to some constraints g equals some value, then the Lagrangian can be written as follows. It's f plus weight a times the g, which is our constraint, and we add on it the equality constraint. Okay, so if we use this formulation of Lagrangian multipliers, the SVM function looks something like this. So we have basically the our value f, which is what we want to minimize, and then we write the constraint in this way, included in the formulation. And the constraint then that we have is that these alpha values have to be greater or equal to 0. So if we take, to find the minimum, if we take the derivative and make it equal to 0, then we can associate the alpha values with the w's and the b's. So this is the primal problem, as it is called. But we will actually solve this equation to find the values of w and b using the dual formulation. So the relationship between duals and primal problems in optimization is that in one case we minimize over some values subject to some constraints. In the other case, we maximize the constraints subject to the previously what we used as previously as the objective function. So we rewrite our equation in a way that uses the alpha values, and again we have the same constraints of the alpha values, and as if you look at it closely, you see that what happened is that the data point values appear in the form of dot products, and this is important for what is coming later. And dot products are often used in recognition since they have they can be interpreted as some sort of a similarity measure. So having dot products in the formulation helps us have an intuition behind what's going on. So in any case, when you have such problems, usually you have some quadratic programming solvers that you can plug them in, and they will give you a solution, basically. So this gives us a solution for the alpha values, and knowing from before from the derivatives the relationship between the w's and alphas, then we can find w and b using these two equations right here, basically. So you can see here that w now it's a sum, it's a linear combination of the data points times their label times the alpha value, which is the weight. So the alpha value is incidentally gets values between 0 and up to the penalty term c. So for if you look at it, the values for which alpha is 0 are the values that do not lie on the boundary. So to say it differently, the values of alpha is not 0 only for support vectors, which are the points that either lie on the boundary of each class or are misclassified. And this is basically a very small fraction of our training set. And this was one of the key benefits of SVM at the time, back in the 2000s, that they were able to remove a lot of the training data and only use a subset of them to classify inputs. So if we write down basically the classification equation of the support vectors, it's given by the same formulation as the linear classifier. So we have w times x times plus b. And basically, if we substitute w for the linear combination of the support vectors, we can rewrite it as is shown there. So we could basically plug in the alphas, plug in the inputs, and classify a new data point x. If the value of the function is less than 0, then it's the negative class. If it's greater, then it's the other class. So here one can be naive in the implementation and either do the sum over all the data points, which basically is you don't have to, since some only have a non-zero alpha. Or you can also just directly compute W once and then use W just as with linear classifier before. So the key thing here again is that the data points that we have from the training set and the support vectors basically, and the input appear in the form of a dot product. And again, you can also pre-compute W to gain speed and be more efficient. Okay, but up to what we've done now, there might be some questions that you want to ask. So the first thing what we've seen is we've seen some points in a 2D dimension. What happens if we have higher order dimensions? So we cannot visualize the data, but for higher dimensions, the answer is that we have exactly the same formulation. The math is the same, and basically we are not talking in terms of lines anymore, but we're referring to hyperplanes. And again, we can find a similar vector W, which has a higher dimensionality. It's not a 2D vector anymore, and exactly the same mathematical formulation applies to what we had before. So with what we have described, what you can do, you can build very powerful detection systems. For example, people have used this. This is the seminal work by Dalal and Triggs in 2005. People have used this formulation to build very accurate person detectors, upright person detectors. Basically, they did it by using Hawk features. They created one big vector. I think it was around maybe 4,000 dimensions or even more. And they created a lot of training data. They fed it through a linear SVM, and basically the output of that was a linear SVM that could classify people, as you can see in the image. Of course, since it relies on gradients, Hawk uses gradients to build the feature descriptor. You can see it may miss some cases. For example, there at the background, the person that's close to the wall, and there's no direct gradient, then it can miss some people. But at the time, this was considered a very seminal work, and a lot of work has gone into this to improve it and go beyond linear SVMs. So another thing is what we just described up to this point assumes that we have linearly separable data. So we need a line. A line can separate our data. But even if we don't have separable data, like in the example in the rightmost figure here, and we have some merging between the classes, we can allow for some misclassification using the slack variables. And then we can also deal with that case. But what we cannot deal with is the case in the middle, where the data is highly nonlinear. So basically, if you have a line here to classify, you will not get an accuracy more than 50%, which is really bad. So at the moment, what we have developed does not work well with very messy data. So how can we bypass this? So the general idea and what is done in the SVMs is that we will use a function f, which we call a mapping function, which will project our data from the input space into what is called feature space or lifting space. And the idea is by projecting to a high dimensional space, we can make the data linearly separable at that space. Okay, so one question is, how can we find this mapping function f? So luckily, we don't have to. We use what is called the kernel trick to basically have this done implicitly for us rather than explicitly. So to do that, we define a function k, which is basically the dot product of two vectors in a higher dimensional space. And you can view this function as a similarity function. So a higher value of this function means the data points are quite similar in the higher dimensional space. So the kernel function basically is the dot product of the two data points, but at the higher dimensional space. So it's defined as the dot product between the two f's, basically, the mapping functions. And one can ask, okay, how do we know if we have a function, if it's an appropriate, if it can do this work for us? So there are a lot of constraints or properties that a function has to have. These are called Mercer kernels, and basically they need to have positive semi-definite metrics of their dot products for all the data points. But okay, this goes beyond this class. Suffice to say that we have a way of knowing when a function is a proper function to be used as a kernel or not. So as an example, look at this function. So we have a kernel that we define as, this is basically what is called a quadratic kernel. So we have a dot product of the 2 points. We add 1 and we square this value. And this is our kernel. So if we assume that we have two vectors, x1 with components x1 and x2, what we need to show is that this function, this kernel function here, is equivalent to the f of x and its dot product with f of xj. We need to show that this is basically, these two things are equivalent. So as an example here to see how this plays out, we have our kernel. If we expand this kernel, it gets something like this. This is just an expansion of the equation. And when we factor in together the different terms, we get one vector transposed multiplied with another vector. So if you look closely, basically this is this can be thought as a mapping function when our f has this particular form here. So if we substitute x into this function, we get the same result, and in this way we show that these two are equivalents. So there is basically a dot product equivalent in a higher dimensional space, in this case in a 7th dimensional space, that can be mapped by this kernel function. Kernel functions can also be valid for a particular range of their parameters. So it doesn't have to be the whole function across the whole range of its inputs. Okay, so we know now what is the kernel trick. How can we apply it into SVMs? So luckily, we don't have to actually change much, because in the formulation we developed with the dual Lagrangian formulation, the two vectors, the dot products between our input and the support vectors appear already as dot products. So we just swap the dot product with our own kernel function, and we basically do exactly the same. We do the linear combination of the support vectors using the kernel function this time. So let's look now at some popular kernel functions that you can use and are available in the different packages. So first one is the linear kernel. So in this case, it's just the previous formulation. We don't have to do anything drastical. We just have a linear classifier. And depending on our features, then this can work well or not work well. So it's depends. Basically, then we leave everything to having a good feature extraction when we use a linear kernel. Another popular kernel is the Gaussian or RBF kernel. Basically, if you make this, if you analyze this term here, you can see where the dot products come from. So that's why this is a valid kernel. And supposedly this this kernel has an infinite dimensionality in terms of its dot product. So, but we don't really actually have to go into infinite dimensions to compute the dot product. It's done implicitly through the kernel. Another popular one is the histogram intersection kernel, which basically works well with the histograms. So for that, you need your data to be scaled and normalized, each value to be from 0 to 1, and the sum of all the components should be 1. And it has been used for different applications like text classification and so on. So it's a useful kernel. So the final question we have to answer is what happens when we have more than 2 categories? So there's no easy answer. As we saw with the linear classifier, what basically we have to do is train multiple classifiers, multiple SVM classifiers. We can follow 2 different strategies. First, we can have the one versus all strategy, where we train for one class versus all the others, or train for every pair of class. And the challenge, obviously, in all these cases is what happens when we have an even number of classes. And if you look at the dimensionality, there are some areas that it may not be clear which of the classifiers is performs better. So basically, solving ambiguities when you have multiple classifiers is the main challenge. Okay, to recap and see an overview of how we train SVMs. So since we're using the kernel, what the software packages usually do is they have what we call, they compute first what we call the gram matrix, which is the dot product of the pre-computed dot product between all the training sample pairs. And that makes dot product basically a lookup operation, even though we can have very high dimensional matrices. But in any case, we first have to define our representation, so we can use Hawk features. For example, we select a kernel function, and when we compute the pairwise kernel values between the labeled examples, and we find the weights and biases and the support vectors. Okay, this is an example for a paper using support vector machines for SVMs, where you can see that the decision boundary is not linear. So in this case, they used a kernel function that was, if I recall, polynomial with degree 2, and we get this kind of decision boundary. And a cool thing to notice is that the non-negative non-faces images look somewhat like faces. So there is some intuition behind what the classifier did there. So when we want to classify a new example, either for example, gender classification or face detection, what we do basically is we compute the kernel values between the input and the support vectors, and we apply the bias after applying the weights, the alpha coefficients, and then we just check the sign of the output. And this is the process of classifying systems with building classification systems with SVMs. So if we use, for example, nonlinear SVMs, kernels basically other than the linear kernel, you may end up with having to do lots and lots of computation in the overall when classifying objects, for example, and images. So one way to speed this up, and we will see later on other algorithms that do the same thing, is to use what we call a cascade. And basically, the idea is that you have multiple SVMs. We use linear SVMs first to classify a lot of the inputs really fast. And then as we progress through this cascade, we discard more and more objects. And at the end, we have a nonlinear SVM that basically addresses the hard examples that the linear SVMs cannot discriminate. And this is basically a cascaded SVM approach. So we can improve the speed beyond standard SVMs. Okay, so closing in on SVMs are a very popular machine learning approach. They have implementation in a lot of libraries like MATLAB and scikit-learn. The idea of using a kernel is very powerful, and it's be used also for other algorithms as well. And they provide a sparse training set representation through the support vectors. And as you saw in practice, they work really well. Some of the disadvantages of SVMs is that it becomes really difficult to use them in multi-class settings, even though there are some formulations. There is no easy way of doing it. Choosing the best kernel that provides the best trade-off can be a somewhat cumbersome way of doing it. So we have to do a lot of experiments to find out what works and what doesn't. And often the case could be just uses better features. Another issue is that at the moment, the packages are so widespread that it's difficult for you to go and write your own SVM. So you rely on on other implementations to do some of the functionality for you, which could be a good and bad thing at the same time. And during training, they require a lot of memory, as I alluded before, that since they have to compute the dot product matrix with all the training data. And when you have a lot of data going to larger scale problems, training can be very slow. So when it doesn't play well, basically with high dimensional and large scale data. Okay, so SVM was basically a very popular classifier, and it was built with strong theoretical foundation. So Vladimir Vapnik and Carolina Cortes that developed SVMs are mathematicians, so they put a lot of work into having solid theoretical foundations, but they were not motivated to a particular vision problem. They were just generic classifiers. So the algorithm we'll see now is motivated more by vision problem, and specifically face detection. This is basically, at its time, was the first, I guess, real-time face detection system that was available. And it was implemented later on in a lot of digital cameras and early smartphones to do face detection. So it was presented by, at CVPR in 2001 by Paul Viola and Michael Jones. They made a lot of emphasis in having a system, a face detection system that can be used in real time on modest hardware. So the main components, which we'll see in detail, are, okay, the face detection, the face images. So it's targeting a face application. The use of HAR-like features for extracting meaningful information from images. The concept of integral image, boosting, and cascade classifiers in more detail this time. So there are three major contributions that they suggested in their paper. The first is for feature extraction, for classification, and how to do detection more efficiently at multiple scales. So they relied on some rectangular features for their feature extraction. They used AdaBoost, which is a boosting algorithm for training their classifiers. And basically their main idea was combining simple classifiers for a more effective detection system. So they relied on boosting to train their classifiers. And we will go into some detail now onto what boosting is. So basically, boosting relates to a series of methods that try to build an ensemble of models that is having multiple models working together to solve a problem rather than having just a single classifier. And the idea is that they want to build stronger classifiers from using what we call weak classifiers. So a weak classifier or a weak learner is basically it's a classifier itself, but the difference is that it's just a bit better than random chance. Okay, so rather than 0.5, which is the random chance, its accuracy could be 0.55 or 0.6 or whatever. And the idea is when you combine multiple of them, you can get something that is much accurate than each individual classifier. So boosting algorithms, what they do, they basically extract formulas for reweighing and combining, how to basically combine these learners together. And one of the most popular and what they use in the paper is called AdaBoost. So AdaBoost is short for adaptive boosting, and it was the first really successful application of a boosting algorithm into a binary classification problem. And on the right here, you can see the outline of the algorithm. So it relies, of course, in having a particular training set of images and labels, which I will go in the process next in a more intuitive example, but just to understand a bit what's going on. Each sample is initialized with some weight. We initially find one classifier that performs, that is more accurate under the current weighing strategy. If its accuracy is over 0.5, then we stop and add it into the pool. We set a weight for that classifier, so how much we basically how much we trust that particular classifier using the previous computed error, and then we update the weight of each sample so that the samples that were misclassified are given higher weight in the next iteration. So after all this process is done, what we get is the strong classifier, where it's a linear combination of the weak learners multiplied by their weight. So looking at a more visualization as an example, so we have our data set here. So we have the positives and the minus data, and all samples at the moment are weighted equally. So we are in the classification process, and we return with this particular classifier. And the error rate of this classifier is 0.3, the weighted error rate, and it has an alpha of 0.4. Then we reweigh again the data points. So you can see here the misclassifications from before have a much higher weight. We compute again the error, the weighted error, and a new weight for the classifier. We do the same thing for the third classifier. And when we combine the three classifiers, we get a much higher accuracy and a much better separation of the classes by just having a linear combination of the weak learners. Okay, so this is another example just to see what the final decision boundary looks like. So it's nothing like the individual weak learners here. So the boosting approach basically tells us how do we select the weak learners to form the strong classifiers. But what exactly are the weak learners? So Viola-Jones used as the weak learning classifier what we call HAR features. So these features are basically motivated by HAR wavelets, and they, if you look at they have black and white rectangles, and their output basically is the difference between the dark regions and the white regions with some weight for each one. And the output, basically, you can look at them as some form of edge or line extractor, depending on if you have 2 boxes or 3 or 4 and so on. So they're applied on one region of the image, and we get a response. So these features, in their paper, they were applied on an area of 24 by 24. This was the data sets that they had, faces of size 24 by 24, and they can appear at different scales within that area, different and at different locations. So in total, there were around 160,000 possible features that could be selected as weak learners. So, and the reason they worked well, especially for faces, is that they were able to capture some general characteristics of faces. So the fact that the eyes are generally darker, the eyebrows are generally darker than the upper part of the forehead. The bridge of the nose could be lighter than what's around it, and so on. So as you can see in the images here, they are basically, there is an intuition behind why they work, these particular features. And at the end, what you get with having a combination of these features is a strong classifier where we get the response of each feature, we multiply it with an alpha weight, and we get the final response. So let's see what the other thing that they propose. So basically, one issue with the in hard features is that because they rely on the differences of regions, we have to sum image parts over and over again. So if we do that in a rather straightforward way, we'll end up losing a lot of computation, doing sums and sums and sums and finding the difference. So what they suggested in their paper, even though I think it was also proposed in previous papers, maybe for some other tasks, they were the first to make it a bit more mainstream, is the concept of integral image. And basically, it can be computed once for an image, and basically is for any given point, in the integral image, it will hold the sum of the areas that are over and to the left of that particular point. So here I think it's much clearer to look at. So the point P holds the sum of all the pixels that are above it and to the left, okay? So the idea was that you do this integral image computation only once, and basically from there on, if you want to compute the sum of a rectangle of a feature, what you do is you just read 4 values out of the integral image. So if you want to find the rectangle, the area of D, rectangle D, what we have to do is read value P4, subtract value P1, P3, and P2. But we also have to add P1 again, so because we have subtracted it 2 times, 1 for P2 and 1 for P3, because it's contained within the sum of those 2 values. And by doing these 4 accesses to integral image, we find the sum of 1 square. If we do another 4 accesses, we find the sum of the white block, and we just subtract, find their difference. So you can see that speeds up tremendously the whole classification process. However, even if these filters are fast to compute using integral image, still a large image has a lot of small windows and a lot of scales that we have to search for. So how can we make this whole process faster? So what they also suggested was to form what is called an attentional cascade. So the key insight here is that in most of the image, we're not going to have a face, or even in more general terms, we're not going to have the object of interest in the whole image. The majority of the image is composed of background and non-class objects. So they proposed this cascade classifier where they basically had different stages of different complexities. So each stage is made up of hard features, but as we increase the number of stages, we allow for more hard features to be used in that stage. And what that does, it makes that particular stage much more accurate, but it makes the early stages much faster, even though they're not that accurate. And where they wanted to go with this is that we have the first stage that's going to be very fast, and we throw out easy negatives. For example, if we have a solid color background, then it can be removed in the first stage. The second stage could remove maybe harder negatives like some lines or some texture in the background. And the third stage, or the nth stage later, is going to focus more on the harder examples that may look like a face or not. So the idea is that you only run these slow classifiers for the promising samples in your in the image. And this is an idea that up to today is used in different contexts. So just to see the impact of this cascade. So if you want to compute the false positive rate of the cascade, then it's the product of each individual stage. So if we, for example, allow for 50% of false positives to be passed through each stage, after 20 stages, we end up with 10 to the minus 6 false positives. And that accounts for for example, if we have a 600 by 600 pixel image, that means we only have, on average, 1 false positive. At the same logic, the accuracy of predicting faces, for example, is again the product of the accuracy of the stages. And after 20 stages, we can have 98% accuracy if we have 99.999 accuracy. If that accuracy drops just slightly, then we can see there's tremendous reduction, almost 10% accuracy reduction in the cascade. but the speed accuracy trade-offs are something you have to deal with in every classifier. So when we have a cascade, one final thing is that during training, we add stages until we reach our predefined goal of accuracy in terms of detection or false positive rate. So putting everything together, we start off by having a database of faces and non-faces. We train a cascade of classifiers using AdaBoost, using the hard features. This process will give us the structure of each stage. So what features, how many features, and the weights of the features. And then we can run this on a commodity computer to get accurate real-time phase detection. And here are some results. This was from their paper. So at the time, people mostly used grayscale images. That's why you see a lot of grayscale in this part of the lecture. You can see it had some difficulties detecting non-frontal faces. So it was mainly done for frontal face detection. Later on, people have worked on it to make it more robust and improve its performance in non-frontal faces. And incidentally, Google also used this technology to blur images in Google Maps, so that your face did not appear on Google Maps. So it had a really widespread impact and popularities. And as I told you, it was implemented in a lot of cameras, and I think maybe even today, a lot of systems use this algorithm. Okay, so looking at SVMs and the Viola-Jones framework, they worked best in the particular papers when we had rigid objects. So we have the view of a person, the view of the face. These are really they were really structured objects and really specific poses of the respective objects. So if you want to have an approach that allows to detect more flexible or objects with that their appearance changes a lot, we need some different approaches. And this is where the bag of visual words comes in. So remember that when we found matches between images for doing depth and motion estimation, the idea in visual words is to do something similar for recognition. So we want a way to characterize the patches of an image in a way that it's easy to match them. Well, as an example here, for example, if we use the SIFT descriptor, so and we have some images in our database, these descriptors land somewhere within the feature space. And we assume here that points that are similar are projected into the same feature space. So when a new image comes in, we first want to look at what patches are in that image, and we want to look if we can find the same patches that we had in the core image in one of the images in the database. So as you can imagine, we can have millions of features to search in our database. So to make the system more efficient, we can take inspiration from other domains. So for example, how documents do text processing and try to match similarities of different documents. So for text, an efficient way to find the pages that where it occurs in is to use an index. So using an index, we want to find in a similar fashion all the images in which one particular feature is visible. And for that, we need to map our features into what is called a visual word. So, but first, a bit more intuition into what is going on here. So let's say that we have this word that we arrange alphabetically, and they appear in, and then next to them is the page that they appear in. Let's say that we're given now these 5 words, and we're asked which page these words appear in. So it's fairly straightforward. Basically, we count the occurrences that each page has for each of these words. So this gives you an intuition into what this is called the bag of words approach, and it gives you an intuition into what we want to do with the bag of visual words. So when we have an image, basically, we have, in this example, 3 different code words. So these are all our features, and we basically arrange them in this space, and we curve up a feature space by finding the mean of each of these visual words. So this basically gives us a mapping of the patches into the visual word space. And it's analogous to the documents, comparing 2 documents. So let's say that we want to compare 2 documents. We don't directly compare word by word. The words are more or less orderless. So we just pick the words and just check if they appear in the document. We don't check if the order is the same. So if you want to do something similar with images, basically we want to find the visual words that appear in each object, and want to cluster them around each of these words around in terms of similarity. And then we have for each cluster one word that one visual point that is the most descriptive. And using that particular descriptive word, we can build a histogram of how much of that particular patch appears in each of these images. And then we can build then a description of each image using this histogram. So let's say now that we want to compare 2 images. What we do is we get the images, we find the occurrences of the visual word in each of these images, and then we do similarity dot product to find how close they are. And the dot product here is normalized by the magnitude of the 2 vectors. So we could also do, this is something similar to nearest neighbors, but we could also apply one of the techniques we learned today, which is, for example, support vector machines. So doing object classification with bag of words, this is a paper from 2004. So in general, when we have the distribution histogram, we can use any classifier that we have learned today. So we take the locations of the images and find the interest points. With that image, we make a description for the new image to find the descriptors that are present in the image, and then we can train based on that histogram a linear SVM to classify new images. This is here basically shows the performance accuracy for different classes. As you can see, there's really high accuracy for a lot of the classes. This is for the CutTech 101 dataset. And in particular here, they used a linear SVM again with the bag of words. So it can give you really good results and you can see that the classes they used, for example, airplanes, are much more diverse in terms of viewpoint rather than faces. So it's a much more challenging environment. Okay, so and this exactly is one of the advantages of bag of words that is flexible in terms of the object shape. It provides us a way to build a compact representation of the image, and as we saw in practice, it gives good results. On the other hand, it might be difficult to find the good visual words if we completely ignore geometry, which is one of the challenges of the approach. And often, if something might pick up that's in the background, so which make the results worse. And still, the way to do the visual words and how to build the vocabulary is unclear. However, it's a very popular method, and depending on the application, can give good results. So, what we've seen up to this point, classification as well as detection, the main goal is to find a class of objects to extract or to identify within an image. It's also valid to ask what happens if we have objects of the same class. So, for example, faces. So let's say what we built a Viola-Jones detection system. We have our bounding boxes, and we extract all the faces. Well, up to this point, all these faces are the same. They are the face class. So what we want to do now is build on top of that and move from face detection to face recognition. That is, we want to distinguish between instances of the same class. And the method we'll see is called EigenFaces. It was developed back in 1990s. It relies basically on a method called principal component analysis, which is a method for dimensionality reduction that is based on the eigenvalue decomposition. And it's called EigenFaces because they use the eigenvector method for faces. And it's also used outside of face recognition as well for different recognition tasks and different data types. So it relies on principal components analysis. So principal components are basically vectors that project the data points to an axis where there is the highest variance in the data. So if you look at this example in the first top figure, you can see that the highest variance is in the larger axis. In the bottom figure, you can see that the second variance is the variance in the second component is much smaller. So they find the direction, the axis in the data set that has the maximum variance. And the idea is that if you isolate these components, then you generate a new space that can be uncorrelated. So we assume that faces lie on a low dimensional subspace that can be determined by the first k, which is a parameter we can choose, and it's much lower than the original image dimensions and dimensionality of the image vector. The first k directions of the maximum variance. So if we want to find those maximum variance, we use PCA to give us those k directions. So we determine the direction that captures the maximum covariance of the data through the eigenvector that corresponds to the largest eigenvalue of the covariance matrix. So we present all the face images in the dataset as linear combinations of the eigenfaces. In that we can make the recognition process much more efficient. So intuitively, the recognition process using the EigenFace method, basically what it does is projects the images into a lower dimensional space, what is called the face space, that is spanned by the computed eigenfaces or eigenvectors. And it was to find in that space the closest match that we have in the database. And this can be done through a nearest neighbor as our classifier method. So looking in more detail, the EigenFaces basically idea is to find a new coordinate system that will capture more the meaningful distributions in the data. So the eigenvectors point to the direction of highest variance in the data, and they can then be used to encompass much of the information contained in the original images. And we can select to use a fewer number of eigenvectors just to have a more compact representation. So as you see here, we have all these images that define one particular space. If we move into the EigenFaces, there is a different space that's defined and is lower dimensions and much easier to find the most meaningful features. So the EigenFaces algorithm assumes a square image. So we have an image of height and width equal to n. We have m training images, and p is a number of persons. So each person has a number of images associated with it. So these pictures constitute our training set, and we assume that they have been taken under the same lighting conditions and are normalized so that the eyes and mouth lie more or less on the same area for all the images. We take that image and we basically turn it into one large vector of dimensionality n square. So then we compute the average face, which looks something like this for a particular data set. And then we find the in the mean value. So we have assumed that we have 8 persons in the data set. We find the mean value for every pixel across the m persons. And then we subtract from each of the faces their mean component. And we do this to move on to compute the covariance matrix. So then we stack each of these vectors, and we compute the covariance matrix by doing a matrix-matrix multiplication. Now, this covariance matrix, as you can see by the dimensionalities here, if you have 100 by 100 image, can be really large. So the computational effort in computing this, not even computing the eigenvectors, is large. Is there a way now to reduce the dimension of the matrix? So thankfully, there is the eigenvalue theorem that tells us that we first define the original covariance matrix. We define another matrix that is basically A transpose times A, which now has the dimension proportional to the number of persons in the image. If we say that V is the eigenvector of LV and lambda V, then the theorem says that A times V is the eigenvector of C times AV equals lambda times AV. So here you can see how this is done. So basically, we multiply both sides here with AV in the original equation here, and we end up having this same formula for eigenvectors. And this is basically tells us that we can just find the eigenvector V for the lower dimensional matrix, and we just multiply that with the matrix A, and we get the eigenvectors basically. And this dimensionality reduction trick, it was what makes this EigenFaces algorithm work. So once we have the eigenvalues and we have the eigenvectors, we sort them in ascending order, and we select a number of principal components k, so that we don't have the total variance is not less than an error epsilon that we select. So these k eigenfaces cannot be used to represent the existing faces in our data set, but as well as new faces. So the eigenvectors of this matrix, that's where the eigenfaces name comes from. And you can see here some illustrative examples. So we have the faces image. These are the some normalized eigenfaces that were selected. And the eigenfaces of this image corresponds to these images right here. And we can view eigenfaces as images because they have, we can map them back into, they have the same dimensionality as the images basically. So you can see there's an eigenvector here that corresponds to the forehead. Let's see, some to the eyebrows, the beard, and so on. So they encode meaningful information of what is in the face. So once we get an image, we subtract the mean, and we take the dot product with each of the eigenfaces, and we get the coefficients that represent this face. Once we have this representation, then basically we can apply some form of distance finding algorithm and check if it's close to a face, which is we can then basically say if it's within a limit, we can just apply it. We can select the face to say that it's that particular face, or we can say if it's a new face, or even if it's not a face at all. Okay, and this can be extended into what is called the eigen backgrounds if you want to find effective background subtraction methods. So eigenfaces have some interesting properties. So if we take, for example, the mean face and add some principal component to it, we can see that we'll get this picture. Now, if we take again the mean face, we subtract a principal component, you can see that we get a similar image where the lightning is inverted. So this tells us that these eigenvectors encode a meaningful information, meaningful variations for what is a face. So another thing we can do is we can reconstruct the face. So when a face is presented, we can decompose it into its coefficients W. If we keep a lot of these eigenvectors, let's say thousands, then we can get a very good reconstruction. As we reduce the number of vectors we keep, then of course the reconstruction is the reconstruction quality is reduced. But let's say there's a side product to this. Let's say, for example, that we give it an image of not a face, but I don't know, an apple or a bicycle, and we decompose it in that way. If we want to reconstruct it back, the reconstruction will not be good because these eigenfaces encode components that are found in a face. So if we try to reconstruct something that is not a face, then the difference between the input image and the reconstruction will be high. So we can use this technique also to validate validate whether we have a face image or not. So EigenFaces provide a very nice way of building recognition systems. The training process is easy to code, and it's somewhat automatic. And once we have the eigenfaces and eigenvalues, then we can be really fast at inference time. And because of the dimensionality reduction, the eigenfaces algorithm can handle large databases. However, as I said at the beginning, the EigenFaces algorithm is not perfect. Basically because we need to make sure that all the images are aligned. So as you can see in the image here, if the faces are rotated or slightly oriented, then they don't align with the other images. So that will make their performance problematic. Also, sometimes the direction of maximum variance that the PCA finds may not be good for discrimination. There are cases that this projection leads to really bad discrimination features. So for this reason, we have some other methods like Fisher faces, for example. And finally, EigenFaces can capture background information as well. So especially if we have images that are not perfectly cropped on the face, then it can lead to problems. So let's do a small recap just to summarize what we saw today. So we started discussing about generative and discriminative models. Generative models during training model the data distributions rather than decision boundaries, and assume that we learn some form of probability distribution. And we can also use them to impose our own prior knowledge on the problem. We test using by finding the probability of an input to belong to one particular class, and we select the class with the highest probability. And some examples are Gaussian mixture models, naive Bayes classifiers, and Bayesian networks. On the other hand, we have also discriminative learning, where during training, what we learn is some parameters that we can use to directly predict the labels from the data. We assume some form of boundary, either linear or non-linear. We have maximum margin classifiers, and we also apply some regularizations to the parameters. During testing, basically, we run the inference with the models and the parameters that we have learned, and it's a threshold-based approach toward deciding the class. And we saw that SVMs and logistic regressions and boosted decision trees and boosted classifiers can yield good results using discriminative learning. And of course, there are many more discriminative classifiers. We'll start looking at neural networks from the next lecture, which is another form of a discriminative classifier. One could ask which one is the best. Unfortunately, the answer is no one knows. It's application specific, and as I alluded to in some parts in the talk, it might also depend on the features that you use, not just the classifier. But in any case, there are some properties that each classifier has that are important to know. So SVMs may require high training times, especially for large data sets, but in the linear formulation, they're fast during inference. We have simpler methods like nearest neighbor and logistic regression. Boosted trees and their extension, random forests, are very powerful classifiers, and they can be used also with limited data. And here are some summary of their basic formulations of each of the classifiers. So the linear SVM, the kernelized SVM, and the nearest neighbor. So what we have learned today, basically we saw some of the techniques that are considered state-of-the-art methods for object recognition. And these were before deep learning methods. They rely on heavily on feature engineering and basically on human expertise to build those features. So the idea up to this point was to design good features, and we can get an off-the-shelf classifier. But developing new features is slow, and the same system and the same approach may not work from one object to another, one application to another, or one domain to another. But they are really useful algorithms, and today, in some under some constraints, they could provide better results than other methods. And they are, of course, very, very